In my Lab 3 video report, I'm going to first introduce the lab and then discuss the physics principles that are involved in the lab, then show my measurements and calculations for the lab, then show the computational model and answer the reflective questions. So the purpose of this lab is to measure the distance dependence of the magnetic field due to the bar magnet, and then compare our measured value of the magnetic field with the calculated value from the computer model. So to perform this lab, we need to first determine the location of the magnetic chip on the device that we use to complete this lab. Then we will measure the on-axis magnetic field value and the corresponding distance. Then we will measure the off-axis magnetic field value with a fixed distance d prime as shown in the diagram. Then we'll calculate magnetic moment from the value we got, and then compute the computational model using the VPython software we used. So a brief overview, the result is n equals to minus 2.1714, and the K, which is the magnetic field, is equals to 1.348 e 10 to the negative 6, and then the magnetic moment is 6.74. So these are some physics principles that are involved in this lab. First is the Bevel-Savart law of magnetic field. Below shows an equation that is provided by our instruction is what this law is about. And then there's the distance dependence of the magnetic field, which is the magnitude of the magnetic field of the bar magnet is equal to K times R to the power of N. And by calculating the log value of our measurements, we could get an expression of ln K versus ln R. And from that, we could then calculate our value of N. And then the last physics principle that are involved in this lab is the Earth's magnetic field. So we need to consider that when we are performing the lab, in order to get an accurate result. So these are my measurements I took during the experiment. From the on-axis value I measured, I could generate the graph on the right to get my n value and my ln k value, which is minus 2.1714 is the n value and minus 13 is the ln k value. And on the bottom is my off-axis magnetic field value, the measurements I got. So I think the graph clearly states what each number means, so I won't elaborate deeply on this. So here's my calculations to calculate magnetic moment. So from the equation, magnetic field of the bar magnet equals to K times R to the power of N, we could calculate the value of K by raising the ln K value to e's power, and then we can get the value for K. And using the value for N and K, and we could calculate our magnetic moment by plugging those values into the equations I wrote on the bottom. So we get our magnetic moment value 6.74. So here's the computational model. The white cylinder represents bar magnet. The orange arrow represents the on-axis magnetic field. The blue arrow represents the off-axis magnetic field, and the green arrow represents the magnetic field at 45 degree. So the calculated value from our computer model is 4.046 10 to the negative 5 and 1.21 10 to the negative 4. And our measured magnetic field value is that 3.84 10 to the negative 5 and 4.45 10 to the negative 5. As we can see, the x component does not have a much difference. And however, y component have a much larger difference than the x component. So this is probably due to the Earth's magnetic field, although I've already subtracted the Earth's magnetic field from my measured value. And the other difference might due to the magnetic field of other objects in my room. However, I think those differences are within an acceptable range. So for the reflective question 1, I think the result will be inaccurate if we don't tilt the phone. Since the magnetic field of the Earth is not cancelled out, then it will add up to the x component of our measurement, which will make our measurements much more inaccurate, since we're measuring the magnetic field of our bar magnet, not the Earth's magnet. And for second question, I think the direction of the result will be the same, but the magnitude of the result will be increased.